Assalamu alaikum viewers, and welcome to the second video relating to the non-terminating integration by parts I method. And as I told you in the previous video related to the same topic, that we are going to discuss two examples over here, and the one we have done in the previous video and the second example we are going to do in this lecture. And as I told you, that if you are trying to evaluate a certain function by taking out its integral in such a way that that function is expressed as the product of two functions, in other words, that if the integrand is expressed as the product of two functions such that both those functions are non-terminating in nature, either if you derivate them or if you integrate them. And the example of such type of functions is over here, you can see. And this is something that I have mentioned already in the first video of my non-terminating integration by parts. So if you're having an integrand which is expressed as the product of your exponential and trigonometric function, in that case you just perform an I method here. And let me tell you in the beginning that I method is a terminology that I'm introducing on my own behalf. It is not mentioned in the books. It is just for my own convenience, okay? So that's it. Now move ahead. And one thing more, that you can have change over here at the place of the angles in trigonometric function. Also, you can have some different powers related to x in the exponential Euler number. So you can have changes right at these positions and nothing else. So let's move ahead and see the second example related to this topic. Okay, so let's have a look. So this is the question and this is the formula of your by parts. Now you see that this integrand is the product of your exponential and your trigonometric function cosine. And you can see, as I told you, that you can have change in the place of your powers. It's not just e of x, it is e power ax. And you can have change in the place of the angle in the cosine. So instead of having cos of x, I'm having cos of bx. So that's the maximum change that you can experience while while dealing with such kind of integrands. So now you have the choice. You can take either exponential function as your f of x, the one that you have to derivate while performing the by parts, and trigonometric function as your g of x, the one that you have to integrate while performing the by parts. You can reverse your choices. It's your choice. It's up to you. Okay. So in both cases, you're going to get the same answer. All right. So I have selected exponential to be my f of x and trigonometric part to be my g of x. Okay, you can swap your choice if you want to. It's up to you. Okay, so your f of x is e of ax and my g of x is cos of bx. All right, and oh, I just forgot to mention one thing, that I have to assume that this thing is my I, okay? I will do it right after finishing up this thing. Now differentiate both sides with respect to your x. You're going to get your f dash x here. Okay, so it becomes f dash x. And you are going to apply a chain rule because the derivative of your exponential is the exponential itself, and then you have to apply the chain rule on the power. Okay, so it comes out to be your a. So the final answer comes out to be your ax. This is your one. So your f dash x finally is this. Okay, so you just highlight this f dash x in a box, and that's it. Now come over here. You have to integrate both sides with respect to your x in order to obtain your capital G of x. Okay, so now you can perform this integral with the help of substitution by substituting bx equals to u and so on, but it's going to further elongate the process your solution works. So just apply the integral directly, and you're going to write that cosine integral is sine of dx. Okay, and in the denominator you are going to take the derivative of your angle. This is it, plus some constant. Okay, and the derivative of this b of x is b. Alright, so it is also, you can handle this thing with the substitution, but as it is going to increase the length of the solution, that's why I just took the direct method to obtain the integral, because you have to perform the integral several times in this question because it is non-terminating. Okay, now you see I just forgot to write in the beginning, so I'm writing over here that I have to assume that this integral entirely is taken to be I. Okay, so let I is equal to your integral e of ax cos of my dx. Okay, dx. This is my I. Now I have to apply my integration by parts formula. Your f and small g are right over here. Your f dash x and capital G of x is right over here. Substitute these values in this formula and let's see what we are going to have. Okay, so let's do it. So that's how we write. Your I is equals to this integral, and over here you just apply your by parts formula. This is your f of x, is your capital G of x minus integral f dash x capital G of x dx. Okay, that's it. Now you see a upon b is something constant, so you just take it outside the integral, and you are I is going to be equal to this thing. A upon b will be written outside, and e of x sine dx. Okay, this is it. Now once again you have to apply the by parts on this integral because it is over here. You can observe that the integrand is the product of two functions still, and both these functions are non-terminating in nature, either if you take out the derivative or integral of both of them. So now once again you just perform your f of x and g of x process. So just take this thing as your f of x, like what you have taken in the beginning, and this trigonometric function, just take it as your g of x and just repeat this process once again. Oh, that's a bird. Depicts that the mango season has started. Okay, now just differentiate. On differentiating both sides, I'm not going to repeat because this is something I have done this already. So I'm going to write it directly on taking out the derivative, and by performing the chain rule, I'm having this answer. Okay, this is my f dash x. Okay, and once you take out the integral at both sides, so my capital G of x is, as I told you, that you can apply the substitution at this place as well. Take b of x equals to your u, and then you perform the substitution process. But as I told you, that it is going to further elongate your solution work. So just apply the integral directly. It's going to be minus of your cosine b of x. In the denominator, you just take the derivative of your angle. Okay, plus some constant. So it is going to be therefore minus cosine b upon b plus some constant. This is your g of x. Okay, so as the process is going on, so you are not going to mention this constant while performing the solution. Okay, so constant is something that you insert in the final answer. All right, but once we are performing the integral, so just fulfilling the formality of the integration, I'm putting this constant over here. Okay, so no need to get confused in that. Now once again you apply your by parts formula over here. All right, so let us see. It's going to be over here I'm going to apply my by-parts formula. So this is my f, this is my small g, this is my f dash x, this is my capital G of x. Let us apply the formula. So f of x and capital G of x minus integral f dash x and capital G of x. Okay. Dx, and you close the bracket. So you see this minus and this minus will become plus, and a upon b are the constant values, will be written outside the integral. Okay, so you have just obtained this. All right, now you are going to multiply this a upon b with both these terms. Okay, and this minus is also going to influence on the signs of the terms inside the big bracket, square bracket, what you say. So therefore your I is equal to your ax sine b of x upon b. Alright, then minus and minus give you plus, and it becomes a upon b square this thing. Okay, then minus plus give you minus. Okay, and a upon b into a upon b give you a square upon b square. Alright, this is it. Now you can see that once again you're having the integrand that was mentioned in the question. Then that was your I, as I told you already over here. So once again you're having your I back. So at this place you're going to replace this integral by your I. Okay, and then you have to shift this I over here the left side, and then we are going to do the work. So let us do it. Let us do this process. So there you go, over here. Now you just shift this I part on the left side. It looks like this, and on the right side just these two terms are left. Okay, now you can take out your I common here. Then I'm having these coefficients left in the parentheses, inside the parentheses, and then I'm going to apply my LCM in the next step. Once when you apply the LCM, it comes out to be this. And over here you can notice that in both these terms you're having e power ax upon b common, so you just take it out just to beautify your work. That's it. So that's what we have. Now you just shift this term on the other side of your equality, so it is going to be inverted then. And let me just organize these the numerator in alphabetical order. That's it. Okay, you can see that this b and this b will get cancelled and over, just one b is going to left. So So finally, you've got your answer of this I integral. That was your question, and it was this. So the integral of this non-terminating integrand has been evaluated by parts by means of your I method, and finally you got a very logical answer of this integral, and you are done. Okay, so that's how you do. So I hope you can see the beauty of this work. So at least I find it very beautiful. So you see it's all done, and I hope this process or this method of evaluating the non-terminating integration by parts has been somewhat clear to you. So you just keep on practicing the questions related to it as much as you can, and try to strengthen your grip on the topic. And whatever you study, just study deeply so that you can gain mastery in that, and you'll be able to forward the topics or the knowledge to the others in much better way. So if you find this video helpful, I humbly request you to subscribe my channel and to share this video as much as you can, and hit on the like so that it becomes more and more, it will spread more and more, and it will help others. Take good care of yourself, and inshallah in the next video we are going to discuss the how to integrate certain functions by means of the process that you call partial fractions. Okay, so I'll see you in future with new helpful videos. Keep in touch. Take good care of yourself. Allah Hafiz.